Um, what kind of answer is it looking for? Because when I look at the why,
Yeah, I don't know. Probably you have to put. I don't know.
seems like that might not be right, but I just want to know what form is.
One thing you can try is putting explicit multiplication signs. It doesn't assume types of octaves. Let's just see.
Yeah.
So you just
Yeah.
All right, good morning, everyone. So same announcements as last time, homework 3 on Friday, labs and tutorials this week. There's no pre-lab this week, but next week you will have to complete pre-lab 1 before you show up to your lab section. Okay, so the sorts of things we've been talking about recently are the electric fields due to continuous distributions of charges. And so the ones that we thought about carefully are the electric field due to a line of charge and the electric field due to a ring of charge. And to calculate these was a little bit of work, right? We had to set up these integrals and it's just, they weren't trivial problems. So what we're going to do is we're going to start to develop some methods that we can use to calculate electric fields in certain situations in kind of a more clever, less difficult way. And in order for us to start to think about that, what we have to talk about is electric flux. And so this is now chapter 6 in your textbook. So chapter 6 of OpenStax University Physics Volume 2. Electric flux is given a symbol. It's another Greek character. We have a lot of Greek characters in electricity and magnetism. And so for electric flux, we're going to use the symbol capital Phi. So it's just a little circle with like a vertical bar through it and then some feet and a hat on top of that vertical bar. So before we talk about what electrical flux is, I thought we would just take a moment to try to think about why we would want to understand this type of quantity. Well, it's going to turn out that this electric flux is going to be a big part of developing this new method for calculating electric fields. And that new method is going to be Gauss's law. And what Gauss's law is going to do is it's going to come up with 2 equivalent ways of calculating the electric flux. One will involve the electric field. And so it's going to allow us to solve for the electric field in certain situations. The other reason we're talking about flux is perhaps even more important. When we get to magnetism near the end of term, we'll talk about a magnetic flux. And it's going to be an important part of Faraday's law. And Faraday's law is going to tell us that if we have a situation in which the magnetic flux is changing, that can be used to induce voltages. And so we can power circuits and devices and things like that using a changing magnetic flux. And so there's really 2 important reasons why we're going to discuss this topic. So to begin, what we're going to do is we're going to recall one of the facts that we established about electric fields. So remember, we drew the electric field due to like point charges, and we said electric fields point away from positive point charges, they point in towards negative charges. And then we actually decided that it's more convenient to draw these electric field lines as continuous lines, as long as we made the important identification that in a region of space, it's the density of the electric field lines that determines how strong the field is. So if you have a little patch of space of some area and we calculate the density of the electric field lines through that area, that tells us how strong the field is. Okay, so let's just remember that. So we're going to recall that the density of electric field lines, and by density, what I'm going to really mean is that if we had like a patch of area, we count the number of lines passing through that area, divide by the area, that's the density, number of lines per unit area. The density of electric field lines, which we'll say is the number of lines divided by the area, is proportional to proportional to the electric field strength. And so we could draw a picture of that. Let's imagine I've got some region of space where the electric field is doing something like this, like it's kind of fanning out as it moves to the right. And so what we could do is we could imagine like a couple of little pieces of area. And so I'll take an area that looks something like this. And we'll say, all right, this little piece of area has 3 lines passing through it. Okay, and so we'll call this, say, area 1. And what I'm going to do is I'm going to just take that area and I'm just going to move it to some other position. I'm going to keep it the same size so that its area A doesn't change. I'll just move it to some position over on the right-hand side. And so this area is, you know, something like this size. These are supposed to be the same. And so this is in position 2, and this is also area A. And this time we have only one electric field line passing through that area. And so what we could do is we could say, well, at position 1, the number of field lines per unit area is 3 divided by 8. And at position 2, it's 1 divided by A. The density of electric field lines is 3 times higher at position 1. And so the electric field is 3 times stronger at position 1. Okay, so in the example above, there are 3 times the number of lines. So let's say electric field lines through our area at position 1 than at position 2. And so therefore we could say that the electric field strength at 2 is 1/3 the electric field strength at 1. Okay, so what we're going to do now is we're going to define this concept of electric flux. And well, let's see, the electric flux phi, so Greek letter phi, is defined to be the electric field strength times the area of whatever surface we're considering. So, I mean, what that tells us already very quickly is that electric field strength is proportional to number of lines divided by area. And the electric flux is going to be the electric field strength times area. So what we're going to have is number of lines divided by area times an area. And so another way of interpreting this electric flux is it's counting how many lines pass through an area of a surface of a certain area. Okay, and so over here we would say, well, at position 2, because we have the same area but the electric field is weak, we have a low flux at 2 and we have a higher flux at 3. In fact, we have a flux of, if we're counting lines, we could say the flux is proportional to 1 at position 2 and proportional to 3 at position 1. All right. So since the electric field strength is proportional to the number of lines divided by area, and the flux is proportional to the electric field strength times the area, that implies that flux is proportional to electric field, and the number of lines divided by the area times the area, which is the number of lines. So if you're given a problem where you have to compare electric flux through a surface, or say through two different surfaces, really what you're going to be doing is counting how many lines actually cross that surface. Okay, so let's do a simple example where we compare electric fields and electric fluxes at different positions in a region of space. Okay, so let's draw a point charge and the electric field that it creates. All right, so let's imagine that we have point charge Q sitting over here, and I'll take it to be positive, so electric field lines will be pointing radially away from this charge. All right, and so I'm going to draw quite a few of them just so that we can have an example with lots of lines in it. Okay, also, while I'm drawing this, I should emphasize that we're always drawing these pictures, like obviously on flat surfaces, on papers and screens and stuff like that. And so they're two-dimensional drawings. But of course, a point charge exists in three-dimensional space, and the electric field lines point radially out in all directions. And so like they would fill a sphere, for example. Okay, so what I'd like to do is place a couple of surfaces in this drawing and compare both the electric field and the electric flux at these two surfaces. So we'll place one over here. And so I'm going to call this surface A. And we've got those lines passing through the surface. And then what I'm going to do is I'm going to place the surface B. And I'm going to place B so that it's the same distance from the charge Q, but it'll have, let's make it a bigger area. So I'm going to put it in some other position, and I'm going to make the area bigger, but the distance from this surface to the charge Q is the same. All right, and so what we're going to do is we're going to compare the electric field at A and B, and we're going to compare the electric flux at A and B. All right. So how do the electric fields compare at A and B? Is A bigger, smaller, or equal to the field at A? Let's think of a point charge. The electric field of a point charge is Coulomb's constant Q divided by R squared. And so if we're the same distance from Q, how does the electric field compare at A and B? They're the same, right? So the electric field at A is equal to the electric field at B because we are the same distance from Q, or we could say that the number of lines per unit area is the same for those two surfaces. Of course, I can't make my drawing perfect, but what I want to imagine is that the density of lines through those two surfaces are equal. So if we have double the number of lines through B, we have double the area in surface B than we have in A. Okay, what about the electric flux? Is the flux at A bigger, smaller, or equal to the flux at B? Yeah.
A is less than B.
Yeah, so all we have to do for comparing flux is count the number of lines. And so we would say in A, we have 3 lines passing through our surface. In surface B, we have 6 lines. Okay, and so flux is proportional to the number of lines through our surface, and there's more lines through B than there is A. All right, so I'm gonna place a new surface, and I'm gonna place this surface over here, and it's gonna look something like this. And so we're gonna have these lines passing through that surface. I'll call it C. All right. So C is further away from Q than A and B. And so is the electric field weaker or stronger at C? Weaker, that's right. So we just look at the density of the lines and we see that the lines are more further spaced out in C. If we just think of a point charge, the electric field is proportional to 1/r squared. So as we move further away, R gets bigger and the electric field gets stronger. Weaker. All right, so then we would say the fields at A and B are equal, but those are also greater than the electric field at C. All right. What about the electric flux? Is the flux at C, which one? It's equal to 1. It's equal to A or B. Which one is it? A. So we're just counting number of lines. Same 3 lines pass through both A and B. And so we would say the flux at A is equal to the flux at C, but each of those is less than the flux at B. All right, so that's kind of the gist of how you can do these simple comparisons. And so it's important to remember the distinction between electric field and electric flux. I think a lot of people who struggle with physics just struggle with keeping terminology, kind of knowing the differences between terms. So for example, like a simple example is when you study kinematics in high school, like often people kind of confuse things like velocity and acceleration, and they use those terms interchangeably or in the wrong scenarios. And so if you just keep your terminology straight and understand that electric field is proportional to the density of lines, the spacing of lines in a region of space, and flux is how many lines cross a surface. Okay, good. So let's see if we can figure out how we can do some more kind of interesting calculations of flux. Or let's just start by seeing if we can understand when flux is large and how we can make it smaller and things like that. So to do this, we're going to start with the simplest possible case. We're going to imagine a uniform electric field that is perpendicular to a surface. So we have a uniform electric field and a surface that is perpendicular to that electric field. So uniform, all that means is that the strength and direction of an electric field is everywhere the same in some region of space. And I'll just draw this as a horizontal electric field. And so I'll draw straight lines that are equally spaced, something like this. Okay, good. And then we're going to take a surface and we're going to make it perpendicular. And so if we were looking exactly at a side view, our surface would just look like this. So we're just seeing one edge of that surface. So we'll call this a side view. And what I'll do is I'll just put some dashed lines just to represent the fact that this really is kind of a surface of some area. And so this is going to have area A. And then we have these lines, you know, puncturing through our surface. Okay, so this is the easiest possible situation for a flux type calculation. We have a constant electric field. It's exactly perpendicular to a flat area. Okay, so in this case, the way you calculate the flux is just exactly the electric field strength times the area. Nothing more complicated than that. So in this simple case, the electric flux is given by phi is just E times A, and that's it. All right, so what do I want to imagine now is that we take this exact same electric field, we take the exact same surface, and all we're going to do is we're just going to change the orientation of the surface. And so if it was perpendicular to the field to start, we're just going to tilt it at some angle. And you could probably guess what's going to happen as I tilt it at some angle. Let's imagine the pivot is on the bottom. So the bottom edge remains fixed, then I just tilt it down. If I tilt it enough, that top electric field line that goes through the area will eventually miss that area as we change its orientation. And therefore, because flux is just the number of lines that pass through, we'll lose electric flux as we tilt that area. And we want to see how we can then correct our calculation. So next, imagine the same electric field and the same surface, except we now tilt the surface relative to the direction of E. Okay, so we'll do the same side view. And we'll draw the same electric field configuration. How many did I draw? 1, 2, 3, 4, 5, 6. Okay. All right, and so now we're going to take our area, and so how many we had? The area went through 4 lines before. Okay, so I'm going to tilt it, and I'll make it a pretty big tilt, I guess. So there's our area A, and what I'm going to do is I'm going to label an angle in here. I'm going to drop down a vertical, and I'm going to say that we're going to have an angle theta with respect to vertical and our surface of area A. All right, and so just looking at this picture, in the first picture, when the surface was perpendicular to the electric field, there's 4 lines going through it, and we could say the electric flux is 4 or proportional to 4. So now we would say, well, we have only 2 lines, and so we have half the flux, but I want to be able to, without having to look at a picture and count lines, how could we quantify this? Well, the way we're going to do it is we're going to try to define an equivalent area. And by equivalence, I mean we're going to define an area that has the exact same flux as the original one, but it's perpendicular to the electric field. If we can find that equivalent area, then we could calculate the flux as just E times the perpendicular area, like we did in the first example. So when the surface
is not perpendicular to E, the flux is reduced because there's fewer lines passing through our surface. Okay, that's fine. We will define an equivalent surface that has the same flux through it. All right, and so let's define that surface right now. That surface is just going to be, if I was to draw like a right angle triangle, form a right angle triangle out of our surface, what I'm going to take to be my equivalent surface area is going to be the area of that vertical section. So I'm going to drop down this thing here, and let me just, this is a side view, but let's just remember that we're talking about a two-dimensional surface. And so there's the two-dimensional red surface, and the green surface would be something like this. Okay, and so we said what we wanted from our equivalent area was to ensure that it had the same flux as the original one. And if I look at the red and green surfaces, they have the same lines that pass through them. They both have these same two lines, and so I'll highlight them. We've got this one and this one through the green surface, and this one through the red surface. And so they have the same flux. All right, what's the relationship between the green line, the red line, and theta? What kind of trig function would we use to relate those? Cosine, right? The green line is adjacent to the angle, the red line is the hypotenuse, and it's the cosine that relates the two. Okay, so the green and red areas are related by cos theta. So in fact, it would be, so the green area would be, let's call it A perpendicular, would be the original area times cos theta, where let's specify now that we're going to call this area A perpendicular. Okay, good. So now we have this green surface that's in a uniform electric field. It's a flat surface that's exactly perpendicular to the electric field. And we know how to deal with that case. We just take A perpendicular times by the strength of the electric field, and that's the flux. Okay, so since A perpendicular is perpendicular to a uniform electric field, we know that phi is equal to E times A perpendicular. That's the flux through the green surface, but that's the exact same flux that's through the red surface. And so this is an expression that's equal for both of them. But A perpendicular is just A cos theta. And that's our expression for the electric flux in a uniform electric field where the area is not perpendicular to E. All right. What we're going to do is we're going to try and express this flux as using vector quantities. Okay, and the reason is it's just for mathematical convenience. Now, the electric field is already a vector. So far, we've only been concerned with the magnitude of the electric field, but it does have a direction. And so that's already a vector. What we're going to do is we're going to define an area vector. So all vectors have a magnitude and a direction. So the magnitude of our area vector will just be the surface area. That part's straightforward. But we're going to have to assign a direction. And so let's think about how we're going to do that. So we would like to express the flux using vector quantities. E is already a vector. So we need to define an area vector. Okay, so we're going to choose the magnitude of our area vector just to be equal to A, the area. We need to now assign a direction. Okay, and for assigning the direction, what we're going to do is we're going to define a unit vector. It's going to be called n hat, and it's going to be perpendicular to our surface area. And so let's draw a picture of what that would look like. So just to be consistent, we'll have the same sort of picture. So we'll start with our uniform electric field, and then we'll put our area in that electric field at some angle. So here's E. And we'll draw our red area looking something like this, like so. Okay, so the normal vector is going to be perpendicular to this area. And so I'll draw it, say, right here. And we'll label this as n hat. And we'll just really specify that it is perpendicular. Okay. So this angle here was theta. I'll draw it on this side just to leave room for our normal vector. And so I think what you could do is you could do a bit of trigonometry and prove to yourself that this angle theta is the same as the other theta that we drew. So those two thetas are the same angle. And what we notice is that this theta next to the normal vector gives us the angle between the electric field E and this new n hat that we drew. So we're going to define n hat to be a unit vector. So it has length 1. That means the presence of n hat doesn't change the magnitude of the vector. The magnitude is always just going to be the area of the surface. It's just there to specify a direction. So define n hat to be a unit vector of length 1 that is perpendicular to our surface. Okay. So let's now consider the expression E dot product with A. Who remembers the dot product? How is a dot product defined? What's A, vector A dot product with vector B? How could you express that in a different way? Dot products. I know you use this in Physics 111. So if I had A dot product with B, how could I express that? Anybody? Yeah. That's exactly right. So A, B, cos theta, and what's the angle theta? It's the angle between the two vectors. Okay, and so now let's go back and look at our electric field and our normal vector n hat. So the angle between the electric field and n hat is theta. So if I want to take the dot product of E and A, what I would do is I would say, okay, this is going to be E dotted with A, and A we said was A times n hat. And so, okay, we could say, well, all right, that's the same thing as A E dot n hat. But you just told me that this dot product is the magnitude of E. So I'll draw it like this, times the magnitude of n hat times cos theta. I'm gonna see if I can give myself a bit more space here. Let's move this down. All right. But the magnitude of vector E is just the strength of the electric field. The magnitude of unit vector n hat is just the length, but a unit vector always has length 1. And so therefore, this E dot A is equivalent to E times A cos theta. And that's exactly what we had for our electric flux. So this is the electric flux of for a surface of area A in an electric field where the angle between the normal vector to the surface and the electric field is theta. All right. So let's just see if this makes sense, right? It's the derivation seemed to be pretty straightforward, not too bad. But what we should do is just consider some extreme situations and see if the result gives us what we think we should get. Okay, so let's think of several cases. So let's test this expression, flux is equal to E dot A is E A cos theta. Okay, let's take the theta equals 0 case. So what we're going to have is we're going to have an electric field that's uniform and theta equals 0. So that means the normal vector of our area is exactly parallel to the electric field. Okay, so then our surface would be like this, and our normal vector would be like this, and theta is equal to 0. Okay, n hat and E are parallel. Okay, so phi is EA cos of theta, but theta is equal to 0. What's cosine of 0? 1. So therefore, the flux is equal to E times A. And that checks out. That was the very first example we did. So that makes sense. All right. So that was a pretty easy case. Let's try another one. Theta is 90 degrees. Okay, so we'll draw our same picture with our electric fields. E. So theta is 90 degrees. That means we have to have a normal vector that's perpendicular to the electric field. And so if our normal vector looks like that, then our surface has to be perpendicular to that. And it's sitting in the electric field like so. What should the flux be in this case? 0. Flux is the number of lines passing through the area. If I arrange my area like this, there are no electric fields passing through that area. So we expect phi equals 0. If we did the calculation, phi is E dot A is, EA cos of theta, but theta is 90 degrees, and cos of 90 degrees is 0. And so we get 0, and that checks out. Okay, just for completeness, I'll draw the last case. So the last case is, let's say theta somewhere between 0 and 90 degrees. That's really the case that we just did above, but we'll draw it again. Okay, so I'll just make some arbitrary angle for my area. I'll draw my unit vector n hat, and this is the angle theta between the electric field and n hat. And now the flux is just going to be EA cos theta, and you'd have to just put in whatever the value of theta is. If it's 45 degrees, cos of 45 degrees would be 1/√2. And so this is going to be a result that's between the maximum of E times A and the minimum of 0. Okay, good. Does anyone have any questions about any of this stuff? Yeah.
Does that mean that the electric flux will not be negative?
So yeah, that's a good question. We could, the way I drew my normal vector in this last example, I made a theta that is between 0 and 90 degrees. I could have drawn a normal vector like this so that the angle here would be more than 90 degrees. In that case, the cosine would be negative. So when we get there, we're not there yet, but we're going to eventually be interested in the electric flux of a closed surface, like a sphere or something like that. And then what we're going to do is we're going to say, when we define our normal vectors, we're going to want them to point outside of a closed surface. And so there, we will worry about whether the flux is positive or negative. But right now, we're not concerned about it. Yeah, does that help? Yeah, yeah.
So the theta we're talking about is from n hat to the line of charge?
No, it's from n hat to the electric field.
Yeah.
Yeah. Yeah, so that's right. So that's right. So if you had, if I have my electric field, I'll just draw one big electric field line, and I have my surface doing this, then I'll draw like a big n hat here. So the theta that we're thinking about is the angle between the electric field and, yeah. Okay, good. So we have, what, 7 minutes left or something? So the only other thing I want to do today is I want to think about what happens if your electric field is not uniform and your surface is not flat. Everything we've done so far is for uniform electric fields and flat surfaces. What happens if we relax those constraints? Like I just said, we're going to want to talk about closed surfaces like a sphere, and closed surfaces cannot be flat. So what are we going to do? All right. So the question is, what if the electric field is not uniform and our surface is not flat? How do we calculate the flux in this case? Okay, so let's just draw a picture of what that would look like. So I'll make an electric field that is definitely not flat. Okay, whatever, something like that. Okay, so this is our electric field, and I'll try to draw a surface that's not flat either. And it won't be perfect, but I'll do my best. Okay, so. And so it's something like that. So there's some curves to this surface, right? These are not flat edges. All right. So what we're going to do is we're going to say, look, I know how to handle a situation where the electric field is uniform and the surface is flat. So what I'd like to do is I'd like to use what I know about that case and apply it here. But I can't apply it to this full surface because I can see that the full surface is definitely not flat and the electric field is definitely not uniform. So the strategy is going to be to subdivide this curved surface into small little patches of area. And we're going to make these patches small enough that I can treat an individual patch as being flat. And I can say that the electric field, although it's changing over a small little patch of area, it's approximately constant. So what we're going to do is to handle this case, we divide the large area into small sub-areas such that each sub-area is approximately flat and the electric field over a sub-area is approximately uniform. Okay, now you could say, well, I mean, maybe there's like an extreme case where the electric field changes very, very quickly over a surface. Well, what you can always do is you could just choose your patches to be smaller and smaller and smaller. Like I've divided this into what, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. I've divided this into 40 patches, but I could just as well divide it into 40 million patches or like a Google of patches, right? You can make the patches arbitrarily small so that you can always get to a point where you can satisfy this condition, these approximations you want to make. And then what you do is you go in and you say, okay, here is my little patch or my little sub area. Let's say I, okay? And so I is just a little index. I have patch 1, 2, 3, 4, 5, 6, 7, 8, 9, up until however many there are. And so if we can satisfy the conditions that we said, approximately flat, approximately uniform electric field, then for sub area I, the flux is, well, we know that it's going to be the flux due to just patch I is going to be the electric field, whatever it is at patch I, times the area at patch I. And what I'm going to do is I'll call it delta A I. So delta A is just a small piece of the total area times the cosine of the angle that the electric field that I makes with the normal vector of patch of area delta AI. So this is patch I of area, let's say delta AI. Okay, I just have 1 more minute left and I'll be finished. So then we could likewise say, this is the same thing as saying the dot product of the electric field at I and delta AI vector. So then what we could do is, so here, this would be, say, n hat I is our normal vector. All right, and so then we could say the total flux is just going to be the sum over all patches of the flux of each of those patches. And so it'd be the sum of all of these. Whoops, this would be a delta A. And then you're in math 101 or math 103 now. You might be talking about limits and Riemann sums. If you take the limit that this patch area goes to 0, infinitesimally small, you could re-express the sum as an integral. And so in the limit that delta AI goes to 0, we could write the flux as the integral of E dot dA. And this is something that we'll use when we do Gauss's law. All right, thanks very much. We'll see you on Friday.